Welcome. In this video, we are going to be taking a look at section 2.11, which is implicit differentiation. So up until this point, we have been working with really explicit functions of x with our derivatives. So we've been able to, in other words, work with functions that are in the form of y is equal to some function of x. We can display that like maybe y is equal to 4x squared plus e to the x, anything that involves just a function of x on that right side. Many times there's going to be cases where we have functions that cannot be expressed explicitly as a function of x, meaning y, some output, is some function of only a single variable x. Sometimes that's going to be really tough for us to do, or it maybe just can't happen at all, where x and y are intertwined in a way that we can actually express them separately. So this kind of necessitates a new way to take a derivative, and we're going to think about derivatives here in an implicit fashion. So when we consider taking a derivative implicitly, what we're really going to be solving for is we're going to be solving for dy dx, the derivative of the y function with respect to x still. But this is going to require a couple things on our part. One is we're going to be required to consider whenever we see y, we want to treat that as a function of x. Therefore, whenever we see a y, we're going to have to apply the chain rule on that term. And we'll walk through individual terms first and then look at kind of full equations and how we would take them implicitly. So generally speaking, though, think of y as a function of x. Therefore, when we take the derivative with respect to x, we need to treat that term as a chain rule term because it's really representing some function, say f of x. So let's go ahead and consider our first few terms here. We're going to jump in. So we want to find each derivative implicitly where y is again a function of x. So the first one, we want to take the derivative with respect to x of 4y cubed. So notice that we are taking the derivative of a y term, but we're taking the derivative with respect to x. This is kind of a new thing for us. So we're taking the derivative with respect to x, but it is a y term. So just like those steps before, we want to consider y as a function of x. And so how we would do that would be considering it kind of as a chain rule. So the outer rule of the chain rule, we'd kind of treat y just like normal. We would consider this as a power rule. We could say 4, if we bring the 3 down as a power rule term here, we could say that would be 12y quantity squared. That would be kind of an outer derivative. But now we want to consider, well, what's the actual derivative of y with respect to x? Well, the derivative of y with respect to x is just dy dx. So we have the outer and the inner chain pieces there. We want to take the derivative on the outside, the outer function, that cubed term, and then the inner derivative is just the derivative of y with respect to x. So the combination of those two terms multiplied together would give us the derivative of 4y cubed with respect to x. Part B, we can consider, well, what happens if we have both x and y involved? Well, this would really be a product rule. We'd have 6x squared could be one piece of this product, and then we could have y as another piece of that product. Those two multiply together. And again, we want to consider this as a derivative with respect to x. So let's go ahead and see if we can apply the product rule with this portion. So first, I'm going to take the derivative of the first term. And again, the ordering here doesn't quite matter as long as you get both parts to this product rule. I'm going to do the derivative of the first term, which would be the derivative of 6x squared, so that's going to be 12x, and then times the second term, which is just going to be y. So the first part of that product rule is just 12x times y. We're going to add to that, well, the first term again, that would be the 6x squared term, and then I'll take the derivative of the last term. So the derivative of y with respect to x, again, we'd call that dy dx. That's the derivative of the y term with respect to x. So both of those derivatives there are in blue for that product rule. And for this, since we're just taking the derivative of that term, we can just leave that just as is there. That would be the derivative with respect to x of 6x squared times y. So we'd use a product rule whenever we have kind of multiple variables multiplied together like that. And the last one we'll do with just that single term is an exponential. How would we consider the exponential with the chain rule here? Well, if I consider first any exponential, we're going to have to apply the chain rule with anyway. We can say that each exponential function, well, we just want to rewrite our exponential. That would be e raised to the y squared. And then we want to take the derivative of that inner function. So we want to really take the derivative with respect to x, and I'll do this kind of in two steps, of the y squared term. So outer derivative, inner derivative would be take the derivative with respect to x of the y squared. And so when I do that, I have e raised to the y squared, that's the outer, and the derivative of y squared with respect to x, we'd say that's, well, 2y would be the outer derivative there, times the derivative actually of the y term, that's the inside function, we call again dy dx. So the derivative of the exponent in general here is going to be the power rule 2y times the inner function dy dx. So putting those all three terms together will be my final derivative there with respect to the x variable. Now let's go ahead and consider how we would go for a full equation here. This is a full implicit equation. We want to go ahead and take the derivative and again find the derivative dy dx through the implicit differentiation process. So the first thing I'm going to consider doing is I want to take the derivative of both sides of this equation with respect to x. And so it's going to look a little bit like this. I'm going to try to squeeze it in as we can here. I'm going to take the derivative with respect to x of this left side. And I'm going to also want to take the derivative with respect to x of the right side. So I'll do that on the same over here. Squeeze that in there. So we have the derivative with respect to x of both sides. At this point, I just want to do kind of two separate derivatives here, one on the left and one on the right. I want to take the derivative with respect to x implicitly on both sides. So let's go ahead and consider the left side alone. The first term we see is the x cubed y term. Again, that's going to be another product rule for us. So we have two terms, x cubed and y. So let's go ahead and apply that product rule. We want to say that that's going to be the derivative of the first term, that's 3x squared, times the second, that's the y. And then we're going to add to that the first term, which is still x cubed. And then the derivative of the y term, we would say is going to be dy dx. The derivative of y is dy dx. So there's my dy dx term popping up for that first product rule. The next term that we'll do, I'll maybe try to highlight this in a different color as we go, maybe in green. We have y squared. Well, if I want to take the derivative of y squared. I think we did that in our last problem when it was in the exponential. We could say y squared becomes 2y with the power rule, but since y is not the correct variable of this derivative, we want to take the derivative with respect to x of the y variable. That would be called dy dx. So we have 2y dy dx for that second term. Okay, so we know that this derivative on the left is going to be equal to the derivative on the right. So let's go ahead and take the derivative on the right side. We'll do 2x. So that's just going to become just 2, because we're taking the derivative with the correct variable here. Derivative of 2x with respect to x is 2. And then we can say subtract that last term. If we do the 4y term, we could say that the derivative of 4y is going to simply be 4. The derivative of the y term is dy dx. So 4 dy dx would be our final result there. Okay, so let's go ahead and analyze what we have so far. We're not quite to our solution because we want to actually go out and find what the dy dx term is representing. It's going to be representing a function of both x and y here. And we'll notice that there's 3 dy dx terms available to us here. So we've got one here. We can highlight here. We'll have one there, one here, and then one on the right side of the equation as well. Our next task is to see if we can actually group these together and then maybe factor out that dy dx term and see if we can isolate that on one side of the equation. So here's where we're going to do a little bit of algebra to kind of finish this problem up. I'm going to maybe bring all the dy dx terms to one side, and I'll do this to the left side, and bring all the non-derivative terms to the right side. They're not constant, but they're just non-derivative terms. So let's go ahead and do that in this next step. So we're going to subtract 3x squared times y on both sides. And I'll just do the sum of the next term in the next step. So we have, especially for this one, just to see it. So those will cancel. We'll be left with x cubed dy dx plus 2y dy dx equals, I'm going to move this to 2 minus 3x squared y, and then minus 4 dy dx. We can now kind of see where we're going with collecting our terms. I want to add 4 dy dx to both sides. They'll cancel on the right, and then we'll be left with our last arrangement. Looking at the left side here, I'm going to maybe make a step here to consider. If we add all of these terms together, notice that each of these terms involves a dy dx now. And so one thing I could do is just factor that dy dx out of all those positive terms. So I could say that this left side becomes dy dx. We're going to have really 4 terms here. We're going to have a 4, and it doesn't matter the order we do this because we're adding them all. We have 4 plus, we have a 3, or x to the third, and then a plus 2y term, all in a row. And then on the right side, we just have those non-derivative terms. So that would be the 2 minus the 3x squared times y. Now that we have those left terms grouped together, we can just divide both sides by the function on the left to get our dy dx on the other side. So we have divide by 4 plus x cubed minus plus 2y should be cubed plus 2y, and then that will actually give us that dy dx term. And maybe write this on the side a little bit cleaner for the last time. So we have dy dx. That is going to give us the 2 minus 3 x squared y. And then we can divide by the 4 plus x cubed plus 2y. So notice that this derivative is dependent on both x and y. So there's two variables that this is dependent on. And we would have our derivative with respect to x here. The next problem that we'll take a look at, we still want to take the derivative implicitly here. This is an interesting problem. X raised to the x, you've probably not seen this function at all in the past, but it's kind of an interesting thing to think about. It's kind of a combination of a power rule and an exponential. You can't really use either rule on both because you got a variable in the base and a variable in the exponent. So there's not really a rule for this, at least in our tool belt so far. And so we need to think about maybe another way to approach this, because we can't use a regular power rule and we can't use an exponential rule. It just doesn't fit. So one way we can approach this is by this implicit derivative technique. We'll have to maybe do a little bit of work on this prior, though, because we'd like to kind of separate the x to the x power and represent it with a log. And so the first thing we can do here to analyze this specific problem is to actually take a natural log on both sides. And we'll kind of see why this is helpful in just a little bit. If I take a natural log on both sides, I'll just get ln of y is equal to ln of x raised to the x power. But we know with natural logs, if you think back to our algebra, that we can use a power rule property and bring this exponent down as a constant multiplier. It's not a constant multiplier, it's just an x multiplier there. But we can do that to a multiplier, so that would become x ln of x multiplied together. Now, instead of a kind of an exponential thing, we now have just a product, everything in the base. This is helpful now because now I could take these both left and the right side and consider a implicit derivative with respect to x. So from here, I can go on both sides and say I want to take the derivative with respect to x, and I'll take the derivative with respect to x of the right side as well. Okay, so let's walk through both sides. Well, the natural log of y, well, normally we'd say that's 1 over our argument. So we'd say that would be 1 over y in this case. But again, we're taking the derivative of the wrong variable here. We want to take the derivative of the y term. So the derivative of the y term with respect to x, we'd call again dy dx. So we have a dy dx term coming in multiplied by the 1 over y. The right side of the equation, we have another product rule on our hands. So we can apply the product rule one more time with just functions of x. So there's actually no y's here. So we can go ahead and just a normal product rule, we could take the derivative of the first times the second plus the first, that's x, times the derivative of the second, which is 1 over x. We can do a little bit of simplification. We'll kind of keep this side 1 over y, dy dx. And then we have ln of x plus x times 1 over x is just going to be 1. So that simplifies nicely. And we'll notice here that we can just multiply both sides by y to get our dy dx back. If I multiply by y, multiply by y, I can cancel those out and just becomes dy dx on the left. So this will be just dy dx, and then we can bring the y to the front if you want. This would be y times ln of x plus 1 in that parenthesis. Another way you could represent this function, notice that the original function was y is equal to x to the x. This is a unique situation where we can actually represent the derivative in really two ways. We could represent it like y times ln x plus 1. That would work. But we also know the value of y here is just x to the x power. So we could actually use that to our advantage here and express this derivative only as a variable of x. Because the original function really was only a function of x. So we could say that this is really x raised to the x and then ln x plus 1. That's another way that you could represent that same derivative, just replacing the value of y back into the equation. So that's kind of a very unique derivative. Y is equal to x to the x using implicit differentiation. Okay, we have one more that we'll go through in this video, and that'll look at an exponential term as well. So part C, we have e raised to the x, y minus x plus y, and then equals x times y. So again, I want to consider taking the derivative implicitly. We have both x and y's, and they can't be separated here. And so let's go ahead and apply our derivative with respect to x on both sides. That would be d dx. And then we'll do a derivative with respect to x on the right. Squeeze that in. Okay, so let's take it term by term. I'm going to do the first term. That's probably the more challenging term, the exponential here. We have e raised to the x, y. So again, when I consider this derivative, the exponential term would tell me to rewrite my exponential function and take the derivative of the exponent, or that inner function. So that's what I'll do here. So rewrite my exponential x, e raised to the xy, and then the derivative of xy we know is a product rule. So if I'm going to take the derivative of xy, I have x as my first term, and we'll have y as my second term. So let's go ahead and get that underway. We'll have the derivative of the first is going to be the derivative of x, which is 1, times y itself would be just 1y. And then we'll add to that x, which is the first term. And then we'll have the derivative of y, which is dy dx. So there we go. So 1y plus x times dy dx. This is going to be helpful because notice on the right side of this problem, if we look over here, that's going to be the same derivative on the right. So that's actually going to be helpful in two ways. Let's continue the process here. We're going to have minus x just becomes a minus 1. And then our last term over here, a plus y, becomes the derivative dy dx. There we go. So we have the full left side. And again, like we said here, the xy product here, we've already taken its derivative. It's sitting right over here. And so we can just repeat that onto the right side. So that's going to just be 1 times y, or we could call that y. And then we'll have plus x dy dx. So be sure to kind of check your surroundings, especially in a given problem, and see if you've already applied that derivative somewhere and could use it again. This is a good chance to take that shot. Okay, it looks like we have some simplification to go, and there's also going to be like 3 dy dx terms here eventually. So we'll want to consider how we might group those once we simplify. So let's go ahead and try to simplify this a little bit before we get to combining terms. So I'm going to distribute my exponential term. So we have y and then e raised to the xy. And then we'll have plus, I'll just write it like this, x times e raised to the xy times the dy dx term. I'll just put that in the back. We'll do this plus, minus 1, excuse me. We'll have minus 1, and then plus a dy dx term. That's going to be set equal to y plus x dy dx. Okay, so at this point, notice that we have, again, 3 dy dx terms. I'd like to group those together, and I'd also like to group the non-derivative terms. So let's start with subtracting those non-derivative terms. I'll go moving those to the right. So that would be subtracting y e raised to the xy, and I'll add 1 to both sides. That would be minus y e raised to the xy, and then I'll also add 1 to that side. So those two moves we could do together. So these would cancel out on the left. I'll be left with, on the right side, x e raised to the xy dy dx, and then plus dy dx equal to, we have a y term plus x dy dx minus y e raised to the xy, and then the plus 1. And it looks like all we need to do at this point is to subtract x dy dx to both sides to get our final result. So I'll go ahead and subtract this term, x dy dx, to group those all on the same side. So I can say that's going to be negative x dy dx. That'll be a plus on the first term there. So those will cancel out. And let's go ahead and consider how we would group this to finish up. So those terms will cancel out. We'll have really 3 terms on both sides now. And we can go ahead and consider how to group the last ones. Notice that a dy dx term here is just going to have really a 1. We'll put that in a color here, a 1 in front of it. So we'll use that as a positive 1 when we group. And we can group in any order here. So if I pull out a dy dx, out of that side we'll have a negative x plus x e raised to the xy, and then we'll have a plus 1. This right side is just all the non-derivative terms. That will be a y, and then we'll have minus y e raised to the xy, and then another plus 1. So a couple terms look kind of similar here, but not quite the same. And let's go ahead and put these all back together. Let's see. I think we're good to go here. So we are going to have, in the end, the dy dx term. If I divide both sides, we'll have that dy dx term with our function of x and y sitting right there. So we'll end up getting dy dx is equal to, we'll have y minus ye raised to the xy plus 1, and then negative x plus x e raised to the xy plus 1. And I think we can call that good. We'll have a function of both x and y for that derivative. So in the next video, we will kind of move a little bit further with this implicit differentiation by looking at finding the equation of tangent lines at a point to a given function of x and y. So look forward to going through that with you in the next video. Thanks for watching, and I'll see you in the next one.